This video series is mainly about how to carry out a basic statistical mediation analysis procedure, but I feel compelled to start with a broader point about the goal of such a procedure in the context of a research program. So I'm going to draw a distinction between statistical mediation, that's the technical stuff I'll get to later, and conceptual mediation, which is what we really want to know about in the long run. The idea that we can help explain why one thing causes another by identifying an intermediate step. The goal of a mediation project is to learn about a process, and a mediation story, a claim about conceptual mediation, takes the following form. X causes Y because of M, which we usually think of as synonymous or nearly synonymous with X causes changes in M, and those changes go on to cause subsequent changes in Y. Claims about conceptual mediation arise from an effort to explain simple cause and effect relationships that have presumably already been demonstrated or at least theorized. So if we represent X causes Y using an arrow like this, then we would represent X causes Y because of M like this. For example, here is a simple causal hypothesis. Coffee causes better math test performance. And here is a conceptual mediation claim extending that hypothesis. Coffee causes better math test performance because it elevates the amount of caffeine in the bloodstream. So the core mediation concept is that X causes changes in M, and those changes go on to cause subsequent changes in Y. And of course, there might be other reasons why X causes Y besides M, so we more often write the diagram using a triangle like this. X causes changes in M and Y, and the changes in M resulting from X go on to cause subsequent changes in Y. Or using the variables from the coffee example, coffee elevates the amount of caffeine in the bloodstream, and the caffeine helps people do better on a math test. But coffee also provides other side benefits like a sense of confidence and good mood that directly help math test performance on their own. This is not the only way to elucidate a cause and effect relationship, but it is a common and intuitive one. When we want to know why one event causes another, we are often hoping to uncover more details about what happens in between them. Unfortunately, it is often very difficult to convincingly demonstrate this kind of relationship. Conceptual mediation is easy to imagine, but hard to test. If you manipulate X, then you can try to show that X can cause changes in M. And you can try to show that X can also cause changes in Y. If you can manipulate M, then you can try to show that M can cause changes in Y too. But when X causes changes in M, how do you know that those same changes are the ones that go on to cause subsequent changes in Y? How can you rule out the possibility that X is causing changes in M and Y for separate, unrelated reasons? You might try to take M out of the picture, stop it from changing, and show that X can no longer cause changes in Y, or at least that the effect of X on Y is weaker under this constraint. But how do you know that your efforts to mess with M didn't also interfere with some other intermediate step between X and Y, maybe the real or more important reason X causes Y? These are very complex questions, and they're just the tip of the iceberg. A research program that seeks to understand a conceptual mediation claim deeply will require many studies tackling the issue from many different angles. For more on this topic, see this paper by Bullock and colleagues. The link is in the description. If we want to study a conceptual mediation claim, one small tool in our toolbox is a statistical mediation procedure, the main topic of today's videos. Suppose you conduct an experiment to test the idea that coffee causes better math test performance. To accomplish this, you must manipulate coffee. That is, you randomly assign some participants to consume coffee and others to consume no coffee. Then you administer a math test. If your prediction is correct, your math test scores should be higher in the coffee condition than in the no coffee condition. Perhaps you also draw some blood and measure the concentration of caffeine in the bloodstream. Then you could also test the claim that drinking coffee causes the body to absorb caffeine. The conventional statistical mediation analysis procedure is designed for this kind of situation, where you have manipulated one variable and measured two other variables that you expect to change in response to the manipulation. If coffee causes changes in the body's level of caffeine, and coffee also causes changes in math test performance, those are both pretty useful pieces of information for this research program. But we can attempt to glean a bit more information from this experiment before we move on to more formal tests of the causal relationship between caffeine and math test performance. And that extra piece of information is that we should expect caffeine to be correlated with math test performance in this study. And not only that, it should be correlated with math test performance even within the group of people who all drank coffee. And assuming there is baseline variability in caffeine, it should be correlated with math test performance within the group of people who did not receive coffee. Some people may have other sources of caffeine. Maybe they had a cup of coffee earlier in the day, and some people's bodies may absorb more of the caffeine in the coffee than others. So there's some variation in the body's level of caffeine within the experimental group and within the control group. And if the mediation story is correct, then caffeine should be associated with math test performance, adjusting for the coffee manipulation. You should be able to fit a regression model with coffee and caffeine predicting math test performance. And the slope of caffeine in that model should be large enough to matter. Of course, even if you do observe this association, even if you find results consistent with this idea, it doesn't mean you have established a causal chain. This hypothetical study could not show that caffeine causes math test performance because caffeine was not manipulated directly. The association between caffeine and math in this study is just correlational, not causal. So you will need to find other ways to manipulate caffeine to shore up your argument about causality. But for now, you're gathering whatever clues you can find in the results of this initial experiment. Statistical mediation analysis is just one tool to gather some clues, and it basically comes down to fitting 3 linear regression models. These videos assume some prior knowledge about linear regression, like you would get from my previous video series. Links are in the description. If you don't feel comfortable with interpreting regression results with multiple predictors, it might make sense to view some of those videos before continuing with the next video in the current series.